Morning, everyone. Hi. Hello. Hi. Can you hear me? Great. So we are here to start a new chapter in our course, Design and Analysis of Algorithms, a chapter on randomization. And randomization means a new way of analyzing algorithms, namely randomized algorithms. Randomized algorithms are allowed to make errors. They are allowed to make guesses, to flip coins as part of the decision and computation process. And if the coins flips come out wrongly, then they could give a wrong answer. And in our analysis of these algorithms, we're interested in two questions. What is the probability for such a error to occur, for such an randomized algorithm to give a wrong answer? And what is the cost, mostly the running time of such a randomized algorithm? And also this running time will in general depend on the outcome of the coin flips. That means it is a random variable. So in order to fully appreciate this chapter number 5, it's very helpful if you recall the basics of probability theory that you probably have learned in discrete mathematics, CS 204, I'm going to say. But we only need very basic probability theory, no advanced measure theory like the advanced courses in mathematics, for instance. Okay, so let's start. And the course, chapter 5, will have the following subsections. We will motivate randomization. We will put it in context to the general computing paradigms. We'll discuss sources of randomness. We will learn about the difference between Las Vegas and Monte Carlo algorithms. We will classify different kinds of errors that algorithms may make, in particular randomized algorithms, and how to amplify, well, not to amplify the error, but to amplify the confidence, so to kind of attenuate the errors. Then we'll discuss a first important example problem, namely Blackbox polynomial tests. We'll analyze this very simple algorithm rigorously using the Schwarz-Zippel lemma. Then we will apply this algorithm to special kind of polynomials, namely so-called TUT polynomials. And we will use this application in order to derive a very efficient and simple algorithm for checking perfect matchings. And we will discuss another famous randomized algorithm, namely for primarily test, so testing whether given integer is a prime number or not. There are two famous such tests that are used intensively. And then maybe we will still also look at the Markov chain Monte Carlo algorithm for the satisfiability problem. So then let's proceed to the motivation. So if you think about it, the early ages of computing consisted of two parts, analog computers and digital computers. And nowadays, most of computers are digital computers, although there's a revival of analog computing actually. But why is it that digital computers have for several decades dominated over analog computers? And the answer to that rhetorical question is reliability. So here you see two kinds of signals. A digital signal consisting only of a sequence of zeros and ones with different, let's say, voltage levels, and an analog signal where not only 0 and 1, but also all values in between can occur. And analog signals were very common from long time. Telephones were analog, radio was analog, television was analog. But analog has the disadvantage that signals generally degrade. Well, that applies to both digital and analog signals. So when transmitting signals, when processing signals, occurs some noise, and the more processing, the more transmission, the longer transmission is, the more noise gets added, and this distorts the signal. And so when you have an analog signal, that means the resulting sound, the resulting image, the resulting data will also be subject to the degradation. However, when we have a digital signal, then even under significant noise, it will still be possible to recover the original digital signal by comparing the value to a fixed threshold. You see this here. Signal has been distorted, but the sequence of bits, ones and zeros, is still clearly visible. That means in digital signal processing, the degradation of the signal quality does not affect the final quality of the audio or video or computation. And this reliability, this is what has made digital computers succeed significantly over all analog computers for several decades. And this raises the question, since engineer has put so much effort into getting this reliability, why would we want to reintroduce unreliability? Why would we want to reintroduce randomness? Or put differently, engineers have put in really huge efforts to get deterministic computation. And to illustrate how successful engineers have been with that, let's consider and count a typical personal computer. Let's look at the CPU. Such a computer, such a CPU, nowadays has easily 10 to the 9 Boolean gates, that is AND, OR gates and negation gates, 10 to the 9, that's 1 billion. And also contemporary computers run at a clock frequency of gigahertz. That means also 10 to the 9 cycles per second, 10 to the 9 operations per second. That means in each second there are possibly 10 to the 9 flips of signals, and in each of the 10 to the 9 gates possibly, that means roughly 10 to the 18 transitions occur, transitions between digital signals and 0 and 1. 10 to the 18, that's an incredibly large number every single second, and none of them fail. That's the highest kind of reliability that humanity has ever achieved. 10 to the 18 operations, flips in each second, and none of them fail. Right? This is really a pinnacle of engineering technology success. However, what I'm saying is not entirely true, to be honest. So here you see such a picture of a computer mainboard with for instance, the memory chips here, right? And already in 1979, Ziegler and Lanford, not related, have observed that cosmic rays can have an effect on such computer memories. Namely, cosmic rays are very powerful um, um, particles, and these particles can flip the charge of 1 bit. So it can flip a 0 bit to a 1 bit, or 1 bit to a 0 bit in such a memory. One of the 1 billion bits could flip, and this will, of course, uh, degrade the rest of the computation. It can invalidate all the computation. And this is not really uncommon. Here's a recent study in collaboration with Google, how frequently that occurs. And these are significant numbers, right? So here, 20,000 times in a year, or here even 50,000 times per year, such a bit flip occurs statistically. And in order to prevent such bit flips, in order to increase the reliability, the determinism of computations, that various measures have been introduced. For instance, error detecting codes and error correcting codes. So error correction in memory, for instance, can be implemented by storing, in addition to the actual data, 1 byte or 1 word, 16 bits or 32 bits, in order to store 1 additional bit, a 33rd bit, in addition to the 32 bits, namely a parity bit, so that when any of the 32 bits get flipped, that results in a discrepancy between the stored parity bit and the actual parity, and therefore such an error at least can be detected. An exception is thrown, maybe a blue screen appears and your computer shuts down, in order to prevent this error to cause any further harm, to maybe even destroy data. So that's error detection in memory to prevent error having bad effects, errors caused by such cosmic rays. And the next level is error correction. So not just error detection, but error correction. But this, of course, requires even more bits, more overhead, makes reliability, makes such memory even more costly. But the baseline for this slide is, since all this effort has been put into making computers so reliably to operate for 10 to the 20 operations without any of them failing, why would we want to revert that and reintroduce non-determinism, reintroduce randomization? And the reason is twofold, well, threefold to be fair. First reason is because it seems like randomized algorithms can be more efficient than deterministic algorithms in some cases. So efficiency. The second reason is simplicity. So for several problems, randomized algorithms and deterministic algorithms, when comparing both, the randomized algorithm is much more easy to implement. Deterministic algorithm has much larger effort in order to program this algorithm. So randomized algorithms tend to be A, more efficient, and B, simpler. So and the third reason, what's the third reason? The third reason is that in spite of all this engineering efforts, still there remains a probability of error. It is still possible, right? It has been achieved to reduce the probability of error, but still it's a possibility. And for instance, with a probability of, I'm going to say, 2 to the minus 100, it is conceivable that your computation actually produces a wrong result, although everything on the surface seems to be deterministic, right? So maybe your algorithm is deterministic, your operating system is deterministic, your BIOS is deterministic, your hardware seems deterministic, but if maybe 2 or 3 cosmic rays hit at the same time, that's unlikely, but possible, then these could still flip a bit and keep this bit flip unnoticed. And that means any randomized algorithm that also has a error probability of 2 to the 100 minus 100, or maybe even less, 2 to the minus 200, will be as good as a superficially deterministic algorithm, because even a deterministic algorithm still has this error probability incurred by possible external events. So from all practical perspective, a randomized algorithm can actually be as good, as reliable as a deterministic algorithm if the error probability is small enough. And we will learn about techniques to indeed decrease this error probability. This is called amplification. So to summarize, the 3 reasons for using randomized algorithms: first, efficiency; second, simplicity; and third, reliability is actually can be made comparable to what superficially seems like a deterministic algorithm. So that's the motivation. And now comes the next question: how can we create randomness, right? So how can we even, if we have a randomized algorithm that maybe flips some coins, virtually speaking, for instance, quicksort, right? You may remember quicksort from CS300, deterministic versus randomized quicksort. How can we, right? So the pivot search in quicksort, in randomized quicksort, is a randomly chosen pivot, right? How can we write an algorithm that performs such a random choice, since all efforts of engineers have been put into removing any chance of randomness as far as is possible from a computer, right? So these are all possible choices of randomness. Look at the bit long enough, and there's a probability that it will flip, and therefore its value could be considered as a random variable, although the probability that it does flip is so increasingly small that it makes no sense in using this as a source of randomness. So now we're faced with the opposite problem. We want to have a source of randomness. We want computer to behave randomly, and randomly here means both unbiased, let's say coin flips should be 50-50, and there should be no correlation between successive coin flips. So we want some stochastic independence. And this is actually turned out to be a pretty serious problem. So we want the computer to part of the computation to be perfectly deterministic, and other parts of the computation want to be perfectly random, right? Not just something in between. And so actually flipping a coin, right? This is far too inefficient, right? This flipping a coin can easily take maybe 1 second, but we want efficient algorithms that run at a clock rate of 1 gigahertz. So we want to be able to flip like billions of coins per second, or more rigorously speaking, we want to have a source of randomness that provides up to 1 billion random bits per second. And this is still not feasible nowadays. So let's discuss some common sources of randomness, some common sources of entropy that are used in randomized computation nowadays. One source of randomized is heat, right? So Uh, Heat means atoms move randomly, and of course the art is in extracting this random motion, because atoms of course are very small, and reading off the motion of an atom, that's very hard. That's actually what Einstein uh, achieved with his famous paper on Brownian motion. Uh, he explained the motion of a small particle in a solution by means of the random motion of the water particles, which are not visible, but the macroscopic particle put into the liquid that has become visible. So heat has been tried to be used as a source of randomness, and the art here is to really extract an entire bit, so that is as much charge as is needed to store this bit in a memory cell from a single atom, uh, which is much smaller maybe than one charge. Next source of input is user input, right? So the user, I'm afraid to say that's you. User behaves randomly in a sense. So for instance, when I move the mouse, the way I move the mouse is unpredictable. If I press keys, then the delay between the keys is kind of unpredictable, maybe less predictable than the actual keys pressed. That's the point of key prediction. So user input, maybe also audio or whatever. But of course, user input, that means the algorithm cannot run independently, and user input could be slow. So that's also not a proper suitable source of randomness. Third source of randomness is quantum mechanics. Quantum mechanics guarantees, that's one of the axiom of John von Neumann's quantum mechanics, that when performing a measurement, for instance at Schrödinger's cat, then there will be an inherent random process, a perfect randomness involved. And this is really the best source of randomness. You may have heard about the um, success of, was it IBM's quantum computer? Uh, this success was actually not about the computation, but about producing perfect randomness. So this is what engineers have been trying to build into our currently fully deterministic computers, some way of reading of random bits using some quantum process. But this is still very slow. This is still far from the billion of bits to be extracted. So currently this is less than 1 million bits. That's I think that's the current world record, extracting 1 million random bits per second. And this is also already only very recent achievement. So that means extracting a random bit is much slower, almost like comparable to access hardware, hard disk access compared to the internal memory access in the memory hierarchy. So because of that, people have been using alternative sources of randomness, which is not actually random, namely pseudo-randomness. So what we want from random bits is we want them to be available at a high rate, number of random bits per second, and we want the bits, of course, to be really random. So that means they should not be biased. There's a famous algorithm of Donald Knuth of removing bias at the expense of requiring more random bits, but producing less biased ones. And we want to have them devoid of correlation. That is, we want them to be stochastically independent. And there's a famous series of tests, particularly in computer science, so-called Martin-Löf tests, that test the randomness of a given sequence. but that's not the purpose of this lecture. Multi-left tests can be learned about, for instance, in theory of computation, CS422. So since sources of real randomness is so hard and difficult and slow, instead what people mostly use even nowadays are pseudo-randomness, pseudo-random sequences. And it's called pseudo-random because at the end it's deterministic. They start with a certain initial value, it's so-called seed, and then from that seed, iteratively calculate the next random value, and so on. And this sequence of values depend deterministically on the seed. So only to us humans who don't know how this sequence is generated, it may appear as being random. So actually it's pseudo-random. So between both extremes, perfect randomness, slow, using heat use or quantum mechanics, and pseudo-randomness, which is actually an oxymoron. It's deterministic, but it is very efficient, right? So one can easily produce billions of random bits using a pseudo-random generator. And as an intermediate, in order to combine the best of both worlds, what one actually usually does is to use true random source from quantum mechanics, let's say, in order to extract the seed. That is costly, but that is performed only once or few times in the algorithm, and then use that seed to create a pseudo-random sequence whose values depend deterministically on the seed, but the seed itself has been chosen randomly. So hopefully that's a sufficiently good source of randomness. And I should really emphasize that it means hopefully there's no proof, no rigorous reason why such a pseudo-random sequence should make any of the following algorithms and any of the rigorous analysis that we will perform actually apply also to non-random sequences of bit flips. So let me say that again. We're going to see algorithms, mostly simple algorithms, mostly efficient algorithms. We will analyze these algorithms, but we will analyze them under the hypothesis that the source of randomness used in these algorithms is actually perfectly random, unbiased, uncorrelated. Whereas if these algorithms are executed, as they actually are usually in practice, if these algorithms are instead executed based on a pseudo-random sequence, then there's no general reason to believe that our analysis still apply. Although in some cases people have been able to analyze such kind of trade-offs between pure randomness and pseudo-randomness and correctness of randomized algorithms. So that being said, let's move on to classify randomized algorithm. There are two famous kind of opposite types of randomized algorithms. But before we look into these two types, Las Vegas and Monte Carlo algorithms, let me remind you of the some basics of probability theory that you might want to freshen up on. So you know what the probability is, right? And in this course, it suffices to consider to know about finite probability spaces. So that's why all measure theory is kind of becomes trivial. You might want to recap what is conditional probability and what is Bayes' theorem here. What is a random variable? When are events, when are random variables considered independent, stochastically, pairwise independence, or general independence? What is the expected value of a random variable? What is the variance of a random variable? So these are technical terms that we will use and in proofs in our analysis in this chapter 5. Okay, now to the two kinds of algorithms. First kind of Las Vegas algorithm, and the second kind is Monte Carlo algorithm. And these names come from these two famous towns that are famous or maybe infamous for all the gambling that happens there. Okay, so Las Vegas algorithm is an randomized algorithm, and remember, in randomized algorithm, two problems can occur, namely the answer, the solution, purported solution of such an algorithm could be wrong, and or the running time of such an algorithm is now in turn a random variable, right? So if we execute the same algorithm again on the same input, so everything is the same, but still being a randomized algorithm, the behavior, the internal behavior, the internal coin flips, and therefore also both the result and the runtime could be different. Let me say that again. Running a randomized algorithm, the same randomized algorithm on the same input data can result in different behavior, can result in different runtime, can result in a different output. And the Las Vegas algorithm is one where the result is always correct. So here, all kinds of undeterministic behavior is hidden in such a way that the result will always be reliable, can be relied on perfectly, but it is the runtime that is now random, that is now a random variable, and therefore we will be interested in expected running time. So the expected value of this random variable runtime, and we will be interested in the variance of this runtime. Right? So for instance, imagining that the expected runtime is very small, then it could still happen that in some runs the runtime is very large, and then we want to know how likely is that such a in some events that the runtime will still be large. How focused around the expected value is the actual runtime, and this is exactly the question about variance, right? Variance captures how much a random variable is centered around its expected value. Is it focused or is it kind of dissipated? That's Las Vegas algorithm, always correct, but randomized runtime. The other Monte Carlo algorithm, it's kind of the opposite type of algorithm in this trade-off between reliability and runtime. Here, the result may be incorrect. So whatever such a Monte Carlo algorithm gives as a result, it is only probably correct, and probably that's something of course we will have to analyze to make it more rigorous. What is the probability for such an algorithm to make an error? On the other hand, for a Monte Carlo algorithm, the runtime is a guaranteed one. This will, for instance, never exceed, never ever, even in a possible unlikely case of the internal coin flips, the runtime bound will always be maintained. So these two types of algorithms, and in order to kind of practice your sense of distinguishing between both kind of algorithms, let's have a look again at the randomized quicksort that you know from CS300, right? As you recall, the standard quicksort, immediate quicksort, is efficient only in the average case, average, not expected case, in the average case for most inputs, but for some inputs, it can be as low as bubble sort. It can have a quadratic runtime dependence, quadratic, right? But if we choose the pivot randomly, then this will be very unlikely. This is the randomized quicksort. Randomized quicksort has running time n log n with very high probability. And so my question for you is this randomized quicksort Las Vegas or Monte Carlo algorithm? Right, so the majority vote, yes, we'll return to that concept, majority. The majority says it's Las Vegas, and indeed that's correct. Why is that correct? Because the result of randomized quicksort will always be correctly sorted sequence, right? The only thing we cannot entirely predict about randomized quicksort is its runtime. If the randomized pivot is chosen unsuitably, that's very unlikely, but it is possible, then even the randomized quicksort will degrade to quadratic running time like bubble sort. This is very unlikely, but possible, and therefore the runtime of randomized quicksort is a random variable, whereas even in this worst case, even then the randomized quicksort will produce a sorted output sequence, so the result will always be correct. Indeed, quicksort is Las Vegas algorithm. Very good, thank you. Okay, let's now move on to discuss possible errors of such Monte Carlo algorithms, right? So this is a slide about errors and probability amplification or reliability amplification for randomized algorithms. And as you probably recall from discrete mathematics, when we talk about decision problems, there are two kinds of errors, false positives and false negatives. So let us formalize a decision problem here for simplicity as a decision problem about natural numbers. So the input will be a natural number, call it x, and the output should be yes or no, depending on whether this natural number x belongs to a certain fixed set L of natural numbers. Imagine, for instance, L to be the set of prime numbers. Then this decision problem corresponds or formalizes the question whether given natural number is a prime number or not, whether given x belongs to the set L of prime numbers or not, and the output will be yes or no. So that's a decision problem, as opposed to, for instance, a function problem where the output could be, for instance, some other natural number. Factoring integers, for instance, is not a decision problem, but a function problem. In factoring integers, the input is still a natural number, but the output is some non-trivial factor of that number. This factor being a natural number, so it's not just yes or no. But here we talk about decision problems, okay? And so the answer should be yes if x belongs to L. The answer should be no if x does not belong to L. And we're going to consider randomized algorithms with one-sided error, and yes, with one-sided error and with two-sided error. And one and two-sided errors come in these two categories, false positives and false negatives. So let's suppose we have an algorithm A, randomized algorithm with one-sided error. And there, that means either the algorithm only makes false positives or it only makes false negatives, but not both. That's one-sided error. So to illustrate that, so the question of false positives and false negatives is also very relevant, for instance, when designing medical tests, right? So for instance, when you're tested for coronavirus, if you have to be tested, then those who design these tests are faced uh, or any other disease, those who design the test are faced with the following dilemma. They cannot be 100% reliability. No medical test can. So could happen that such a test gives false positives, that means the test could say, yes, you have this disease, corona or whatever, but in actually you don't. That's a false positive. Or the test could say, you don't have this disease, but actually you do. So the test misses occurrences of the disease. That's a false negative. Or the test could detect the disease where actually no disease is present. That's false positives. And ethically, this is a very subtle point, right? So because a false positive creates a lot of anxiety, right? So for instance, you suppose you go to a clinic and you get tested and the doctors say, well, you have this disease, and immediately you start worrying, right? And then maybe later it turns out that this was a false positive, but all the stress in between. On the other hand, false negative can be very dangerous, right? The test says you're healthy, nothing to worry about. So you start going to Itaewon dance, but actually you are infected and you create a cluster infection. So false negatives are also a problem, right? And so there's a trade-off between both. Um, and the same applies also to randomized algorithms. So let's consider, for instance, this randomized algorithm with one-sided error that makes, let's say, only false negatives. And let's say the error probability is P, and P is less than 1, right? So what does it mean if the error probability is equal to 1? That means the algorithm doesn't even look at the input, right? It just flips a coin anytime. Such an algorithm is of course useless, an algorithm with error probability equal to 1. So the reasonable algorithms or useful ones have error probability at least less than 1. Not necessarily very small, but just less than 1. And now we see a simple technique on reducing that error probability to become as small as we like. Maybe that's by repeating this algorithm. Well, let's take this algorithm with only false negatives and repeat this algorithm, let's say k times, where each new execution, remember, could give a different outcome, because each execution, the algorithm will flip a new set of coins that whose outcome could be different from the previous execution. And most importantly, we suppose that the next execution will be stochastically independent from the previous one. That will be important in our analysis. So we repeat this algorithm k times, and if all executions of this algorithm say no, right, then our algorithm will also report no. But if any of these k executions says yes, then our algorithm will stop performing more executions and just say yes. And recall, false negatives means that when the algorithm says yes, this can always be relied on. Only the answer that cannot necessarily be relied on is well when the algorithm says no. So if we execute the algorithm k times and any of these k executions says yes, then our new meta algorithm will correctly answer yes. And the question is, what is the probability of our meta algorithm to give the incorrect answer, no? And for this to happen, that means that all k execution of the original algorithm must also have made an error. If any of the k executions gives the correct answer yes, then our new algorithm will also give the correct answer. Or put differently, for our new algorithm to give the wrong answer, it is necessary that all k executions give the wrong answer. But one execution to give the wrong answer occurs with probability p, according to our hypothesis. So for all executions, all k of them to give the wrong answer, since they are independent, recall, that means that all of them must give the wrong answer with probability p, and that occurs with probability p to the k, right? That's basic probability theory. Repeatedly giving the same, in this case, wrong answer, an event to occur repeatedly, independently, then you multiply the probabilities, and in this case, we multiply p by itself k times, so the probability will be k p to the k, and since p was less than 1, p to the k will be much, much less than 1, and as we increase p, this probability will tend to 0, will become arbitrarily small. Just to consider an example, let's say that the error probability is 1 over 2, 50%. And if we repeat this algorithm 100 times, then the error probability will be 2 to the minus 100, right? And I recall this is comparable to the deterministic algorithm to fail, right? So that, as I said before, we can make even a randomized algorithm in this way, have a error probability still positive, but arbitrarily small, in particular smaller than the error probability of what superficially might seem like a deterministic algorithm. So this is our first technique of probability amplification. Improve the reliability of algorithms with one-sided error. In this case, algorithms having false negatives only. And you can simply treat the case where the algorithm A has false positives only. Then, yeah, I leave that to you to figure it out, okay? So, well, what if the error probability is not 1 over 2, but let's say 99%? Then still, we just have to perform even 0.99 raised to sufficiently high power will be less than 50%. So for all practical purposes, we only need to repeat such an algorithm a constant number of times to make it as reliable as a deterministic algorithm. So that's some case of one-sided errors. So this is kind of like you can consider this as a trade-off, how to turn a Monte Carlo algorithm into a Las Vegas algorithm. We start with an algorithm that may make error, but let's say has a bounded runtime, fixed runtime. Then we repeat that algorithm. So we increase the running time, and in order to decrease the error probability to make it as good as a deterministic algorithm, a Las Vegas algorithm, but now the running time kind of increases. Let's consider algorithms that make two-sided errors. So possibly both false positives and false negatives could occur. What are we going to do in such a case? Let's suppose we have such an algorithm at our hand, and observe that also in the previous case, we don't even need to know the algorithm itself. We can just repeat the algorithm blindly as a black box. And this is also what we're going to do in this second case. We are going to repeat the algorithm again k times, but now we're going to report the majority answer. So among these k executions, if more than 50%, if more than k over 2 times the algorithm says yes, then also our new algorithm will say yes. If more than 50 times the algorithm says no, then also our new algorithm will say no. And I don't want to discuss the case of type breaking. So let's just say that k is an odd number, then it always will, one of the two answers will have the majority. And we want to analyze the probability of this new meta-algorithm that repeatedly performs algorithm B and then reports the majority. We want to analyze the probability of this algorithm to fail. To this end, let's again suppose that the original algorithm has some error probability P, and here we need to suppose that this error probability is strictly less than 1/2. Why strictly less? In the first case, we only need to require, in one-sided error case, we only need to require that the error probability is strictly less than 1. Here we need to require error probability strictly less than 1/2. And the reason here is, if we allow error probability equal to 1/2, 50%, then an algorithm can easily achieve that by simply flipping a coin without even looking at the input, right? So when flipping a coin to determine the answer, yes or no, this answer will be correct with probability 50-50, right? Without even looking at the input data still, this will be correct. But of course, such an algorithm is useless. By simply flipping a coin, any answer that can be determined by only looking at the coin without looking at the input, that's unreasonable. So we really need the requirement here for the error probability to be strictly less than 50%. And now we want to analyze the error probability of the derived algorithm, one with the repeated execution and majority answer. And to this end, we're going to use a tool that you may or may not be familiar with from stochastics, namely Hoeffding's inequality. So what is Hoeffding's inequality? That's a theorem from pure mathematics, right? So says nothing about computation. Instead, it is about k independent random variables with values between 0 and 1. Right? So we have these random variables x1, x2, x3, up to xk, and these are supposed to have values between 0 and 1. For instance, they could be coin flips with values just 0 and 1, but they're also permitted to be any real number value between 0 and 1. We're going to consider the sum of these random variables, which is now a new random variable, and let's call this x bar, the sum of these random variables. Then Hoeffding says that if these original random variables are independent with values between 0 and 1, then the probability that the actual sum random variable exceeds the expected value, right? So probability expected value of the sum random variable compared to the actual value, the outcome. This is a new random variable. The difference between both is a new random variable, and the probability that this random variable has a value exceeding k times t, where k denotes the number of original random variables and t denotes any positive real number. This probability is less or equal to e to the exponential function 2 minus 2k t squared. Okay, so that's a purely mathematical statement about probability, and we're going to apply this statement to specific choice of independent random variables in 0, 1, and to a specific choice of t, and k in our application denotes the number of times that the algorithm B is executed. Namely, let xn be the random variable that the end execution of the algorithm B errors, gives the wrong answer. Right? That's a random variable. It's 1 if the end execution gives the wrong answer, and it is 0 otherwise. So this is kind of a Bernoulli random variable with values 0 and 1. And the n plus first execution is independent of the end execution, right? So the n plus first execution flips its own set of coins, which are therefore statistically independent of those flipped in the end execution. So these random variables are indeed independent, and therefore we can apply Hefting. The hypotheses are satisfied, and we're going to apply Hefting with the value t equals 1 over 2 minus p. Now recall that we have supposed that p is strictly less than 1 over 2. Therefore, 1 over 2 minus p is strictly positive. So again, also this hypothesis of Hefting's equality is satisfied. And what does Hefting then say? So Hefting then predicts, let's apply this and look at the part in the probability. Hefting says the probability that what? That the total number of errors, right? So the sum, each random variable is 1 if the end execution is an error. So the sum means the total number of errors made in executing this algorithm B minus the expected number of failures. What is the expected number of failures? Well, each algorithm, each execution is supposed to fail with error probability P, and by linearity of the expectation, therefore the expected number of failures in the sum is K times P, right? Each one failure probability P, failure probability P, failure probability P. Therefore, the expectation of the sum is K times P. And this is the actual number of errors. So this is the difference, means that the number of failures exceeds K times P by at least 50% minus P times K. Or put differently, what this event here means that more than half of the executions give an error, right? So this is the actual number of errors. This is K times P. This is K times 50% minus P. So by rearranging these terms, this means that the number of errors is more than half, more than K over 2, more than 50% K. So this is what we're interested in, right? Namely, the event that more than half of the executions give a wrong answer. This is precisely the case when our new meta or derived algorithm gives the wrong answer. When more than half of, when more than the majority, when more than half of the execution give a wrong answer, and this is exactly this term in the probability, and Hefting says this probability is less than this expression. So now let's plug in the value. So t is 1 over 2 minus p, so it's strictly less than 1 over 2, right? So that t squared is strictly less than 1 over 4 times 2. So that this expression means e to the minus k over 2. Then, according to Hefting's inequality, the probability for our derived or meta algorithm to give a wrong answer is, well, right-hand side of Hefting's inequality, e to the minus k over 2 for our choice of t. Or put differently, if we repeat the algorithm B 200 times, then the error probability will be less than 2 to the minus 100, right? So E is greater than 2, and K 200 divided by 2. That means the error probability will be less than 2 to the minus 100. So again, we will be in the same realm as superficially deterministic algorithm. The probability for our repeated algorithm error probability will be comparable or less than the error probability, the probability for a deterministic algorithm to give the wrong answer due to cosmic rays. So for all practical purposes, again, by repeating an algorithm with two-sided error sufficient number of times, we can, in reporting the majority answer, we can amplify the reliability to make it as reliable as we want. Okay, so let's move on to the last slide for today, namely first application, a randomized test for the black box polynomial identity problem. What is the black box polynomial problem? So we're given a polynomial, but we don't know which polynomial. We cannot look at the polynomial. We cannot look at the coefficients of the polynomial. We only can evaluate the polynomial. And we're supposed to answer whether this polynomial is the zero polynomial or not. That's a decision problem, right? So let's just, for instance, imagine that I have hidden this polynomial here in my pocket, and you're supposed to find out whether the polynomial I've hidden is a zero polynomial or not. And you can ask questions, but you cannot ask about the coefficients of the polynomial. Then it would be easy, right? Just ask, is the zero's coefficient zero or not? Is the first coefficient zero or not? And so on. And after this, having asked all coefficients, you can easily see whether this is a zero polynomial or not. But that's not how this problem works. The only thing you can do is evaluate this polynomial. So you give me a value, and I will tell you what is the value of this polynomial. So let's say, for instance, you give me x equals 5, and I will tell you my polynomial p of 5 has value 0. Okay, then you can ask me another argument, let's say 3, and I will tell you my polynomial when evaluated at 3, p of 3 is 7. Then what will you answer? Right, exactly, Adil. If you query my polynomial at the value 3 and I tell you the value at 3 is 7, then certainly this is not the zero polynomial, right? If it were the zero polynomial, then the value would always be 0. So this is a kind of a problem with one-sided error, right? So when the answer turns out to be non-zero, then indeed you can be sure that the polynomial is non-zero. However, if I keep answering 0, the value is 0, then you cannot be sure, right? You could have accidentally hit a root of my polynomial. A root of my polynomial means at this argument x, the value is 0, but the polynomial itself is not the zero polynomial. You've just had bad luck hitting a 0 of my polynomial, right? This is kind of like, do you know the game 20 questions? In the game 20 questions, I imagine a number, and you're allowed to ask whether this number is greater or equal to, or greater or less than a certain number you can query. Let's play this game 20 questions. Let's play 20 questions. So I've imagined a number And now you can ask question about that number, whether my number is greater or less than a number you can say. So first question. Great, Kim Jong-un. Yes, you've got the idea. Yes, my number is less than 100. That's your first question. Next question. So In Young asked whether it is less than 50. Second question, and my answer is yes, it is less than 50. Eugene asked whether it's larger than 0. Okay, I should have told you it's a natural number. So yes, it's larger than 0, and Eugene's answer is not charged. So for it's still two questions. And the third question is asked by Hyun Ji-hun. Is the number greater than 25? Third question. My answer is no. So In Young asked whether it's less than 12. And yes, it is less than 12. Fourth question. Adele asked whether it's less than 6. Fifth question. No, it is not less than 6. Less than 9. No, it is not less than 9. Okay, anyway, yes, less than. So I've imagined the number 9 equal to 9. But yes, you get the idea of the game, right? And this is a kind of similar game that occurs with Blackbox polynomial test. I have this polynomial here at me. You don't know the polynomial, but you're allowed to ask certain questions. You are to ask only certain questions, namely questions about the value of the polynomial at certain arguments. That's the idea, okay? Good. And the generic Blackbox polynomial test algorithm for the unknown polynomial p is the following. We fix a set D, and the algorithm guesses possible arguments, so not deterministically, but randomly choose some argument x uniformly at random. Uniformly means every element in D has the same probability, so D is supposed to be a finite set. And then query me, what is the value of my polynomial on this argument x? And if I say it is 0, then the algorithm also says 0. And if I say it's non-zero, then the algorithm says the polynomial is non-zero. This is a great example of an algorithm with one-sided error. Namely, when the algorithm says non-zero, then that's always correct. The algorithm says non-zero only when it has found a witness, an evidence, a certificate for my polynomial to be non-zero, but the algorithm could make errors saying that the polynomial is 0 if the algorithm hits samples the root x. Then it could still be the non-zero polynomial, but when evaluated on the root, it is the 0 polynomial. So, and our goal is to analyze this Blackbox polynomial test algorithm. Now, in general, one cannot say anything about the error probability because, I could always make up with the polynomial in such a way that it always hits, that your questions are always roots of my polynomial, right? I could kind of cheat. I could adaptively alter my polynomial. So you ask your first question and they say this is a root. Then you ask your second question and I also make this a root by just, multiplying the linear factors. I can create on the fly polynomials larger and larger degree that has roots at all the values that you question, but still is not the zero polynomial, right? So in order to prevent this kind of cheating, we're going to impose a constraint, a promise. I promise you that the polynomial I'm thinking about has degree at most 6. Well, not necessarily equal to 6, because it could be the zero polynomial, right? The degree of the zero polynomial is minus infinity. Degree of a constant polynomial is 0. Degree of the zero polynomial is minus infinity. But when I promise that my polynomial has degree at most 6, then I can kind of trick you at most 6 times, add at most 6 roots, and then I've reached this degree constraint and cannot add another linear factor, right? And this is in general the case because of the well-known, actually the easy part of the fundamental theorem of algebra. Any non-zero univariate polynomial of degree at most d has at most d roots. So if you ask me any d different arguments, no, actually, if you ask me any d plus 1 arguments, then at least one of them will not be a root, and therefore, after you have asked me d plus 1 different arguments, then you will have received a certificate that the polynomial I'm thinking about is not the zero polynomial. But yeah, as I said, this observation, this analysis means that the generic black box polynomial test algorithm will succeed when we have a univariate polynomial, because the fundamental theorem of algebra applies to the univariate case. Polynomial of degree at most 6 has at most 6 roots. But what if we have a multivariate polynomial? Let's say a polynomial in several variables. For instance, let's say 2 variables. So here, for instance, is a polynomial in 2 variables, right? X squared plus y squared minus 1. What's the degree of that polynomial? It has degree 2. How many roots does it have? How many roots does this polynomial of degree 2 have? Infinitely many. Very good, Adile. Right. So here are the roots, right? The roots of this polynomial are precisely all numbers on this circle. And there are infinitely many numbers on this circle, right? So that means that the fundamental theorem of algebra becomes blatantly wrong when we proceed from the univariate to the bivariate case, and even more so when we have the multivariate case. So our goal for the next lecture on Thursday will be to analyze the error probability of our generic black box polynomial test in the multivariate case. The univariate case being trivial, being easy, but the multivariate case, that's interesting. So that's all for today. Thank you very much for your attention. We will continue on Thursday learning about the design and analysis of randomized algorithm. And as usual, I'll stay online a few more minutes, and while the TAs take over and answer your questions concerning homework or other administrative issues. Thank you.